well, both people are here, right?
Yeah.
So I guess we can start then.
You have one person online as well.
Okay, yeah. All right, so welcome to part 2 of me being here. Last time was econ, which was fairly straightforward. This time is environmental engineering, which maybe is not so straightforward. Most of civil engineering is applied physics. Environmental tends to be applied chemistry. And so environmental is the discipline that people tend to grumble and dislike the most. So to begin with environmental, we have to begin with some chemistry. So let's look at a simple, straightforward problem. And let's say that we have glucose. And we're going to oxidize it. And it's going to go all the way to carbon dioxide and water. So the first thing we need to do when we look at an equation like this is kind of ask ourselves, is it balanced or not? We need to make sure that the equation is balanced. And by balanced, we mean, do we have the same number of elements on either side of the equation? And so when we're dealing with sort of chemical reactions, we kind of look at the important species. In this case, glucose is kind of the one that we care most about. And so on problems like this on the FE, what you generally would do is say, okay, this first species, let's make it stoichiometric coefficient, let's make it a 1. And then we simply look at balancing all of the other elements based upon making glucose a 1. And we will get stoichiometric coefficients for oxygen, for carbon dioxide, and for water based upon that. And as we balance, the general rule is balance every element except for oxygen and hydrogen, balance hydrogen second to last, and then balance oxygen last. So this O2, the oxygen here at O2, that's going to be the species that we're ultimately going to balance at the very end. So if we look at an equation like this, we see that glucose has 6 carbons on the left. We have 1 times 6 of them. So on the right, we have to have 6 carbons. So carbon dioxide, its coefficient must be a 6. Likewise, on the left, we have no other species except for oxygen and hydrogen. So let's do the hydrogen. We've got 12. 12 times 1 is 12. On the left, we must have 12 on the right. H2O has 2 hydrogens. 12 divided by 2, we're going to have 6. And then at the end, we balance the oxygen. And we look on the right-hand side, and we say, OK, I have 6 times 2. I have 12. I have 6 times 1, I have 6. On the right, I have 18, which means on the left, I must also have 18. But there are 6 already in glucose. 18 minus 6, 12. I need 12 oxygens, O2. Subscript is 2. 12 divided by 2. We need 6 oxygens. So if we were balancing this equation, this would give us a nice balanced form of the expression. Now the problem is chemists use moles and molarity and all those fun things. Engineers tend to work in masses, so we need to convert stoichiometry then to mass, and we'll do some sort of mass balances. So if we wanted to know how much oxygen does it take to consume so much glucose, what we would have to do then is convert everything to mass, and we would work with the molecular weight. And so the molecular weight of glucose, what is glucose? C6, so it's going to be 6 times the atomic weight of carbon, which is 12, plus 12 hydrogens, 12 times the atomic weight of hydrogen, which is 1, plus 6 times the atomic weight of oxygen. Oxygen weighs 16. Math, math, math. We get 180 grams per mole. So 1 mole of glucose is going to weigh 180 grams. Likewise, we do oxygen. Oxygen is easy, O2. That's going to be 2 times 16, 32 grams per mole. And then if the question asks, how much oxygen do we need per gram of glucose, we could say, all right, 1 gram of glucose times, now we need to look at molecular weights. Glucose weighs, what does glucose weigh? Glucose weighs 180 grams per mole. So we would say 1 mole divided by 180 grams. How much oxygen do we need? Well, times 6 moles O2 for every 1 mole of glucose. And then oxygen weighs 32 grams per mole times 32 grams per mole. Math, math. We ultimately get then that 1 gram of glucose requires 1.07 grams of oxygen. So we have to be conversant with chemistry. We have to convert from moles to grams, grams to moles, back and forth. And we need to use the stoichiometric coefficients to carry out that, enable it to work. Yeah? So fundamental chemistry is important. And as we kind of go through environmental problems, we see that chemistry shows up a lot of different ways. And we end up doing a lot of conversions between various species. And I kind of jokingly tell my students in the environmental class, the #1 rule of environmental engineering is just, when in doubt, cancel units out. Environmental tends to be a lot of looking at units, what divides by what gets multiplied by what, so we get the correct unit in the end. So if we look at water quality and we kind of say, okay, what are the major species that we expect to see in water? If we look at the top 7 or so, the major cations we tend to see are calcium, magnesium, sodium, and potassium. The major anions tend to be bicarbonate, sulfate, and chloride. Typically, when we are looking at these species and we talk about them in problems, concentrations are given in terms of milligram per liter. Most of these species exist at the milligram per liter range. But then if we want to do anything with it besides the most simple of calculations, we need to convert it to some unit that perhaps is a little bit more convenient or easier to work with. So oftentimes we need to put things in molar units. Which would be, moles per liter. And we would take our milligram per liter concentration, we would divide it by the molecular weight, which has units of grams per mole. We recognize that gram per mole, we could just do milligram per millimole, put a little m. The milligrams cancel out. This is going to give us millimole per liter. Molar units are useful if we're dealing with stoichiometry and chemical equations. All the equations are written with stoichiometric coefficients that are based upon moles and not based upon mass. So we need to use molar units to solve any problem that involves a chemical equation. We will also occasionally see problems that use a different set of units. They use normality or equivalence. And to convert from moles to equivalent units, we would take our concentration millimole per liter. We then would multiply it by Z, where Z is the valence. Z would have the units equivalent per mole, or in our case, we could say milliequivalent per millimole. And the moles cancel out, and we're left with units milliequivalent per liter. Equivalent units are useful, and we talk about them a lot when we talk about hardness, alkalinity, these things which we'll get to in a few minutes. So molar units are important. Equivalent units are important. We can convert directly from mass to equivalence by using the concept of the equivalent weight. The molecular weight divided by its valence, that's going to have units grams per mole divided by equivalent per mole. That's going to have units then of gram per equivalent. And this expression, molecular weight divided by Z, that's what we call the equivalent weight. So why does any of this matter? What do we care about it? Well, oftentimes we might see a problem like, what's your best estimate at the missing species in water? And one of the ways we could approach a problem like that is to use the concept of electroneutrality. And electroneutrality essentially says that all of the positive charge has to equal all the negative charge. Or generally, the sum of the cations equals sum of the anions. Now, the important thing is, since this is based on charge, the easiest way to carry out this math would be to convert everything into milliequivalent per liter. And if we're working in milliequivalents, then we know that a calcium and a sodium, we've already converted them into a charge basis, so we can easily do the math in terms of equivalence. Otherwise, we would have to do a more complicated expression for molar units. We would say 2 times calcium plus 1 times sodium, because calcium has a charge of 2, sodium has a charge of 1. Another thing that we are concerned about in terms of water quality would be the concept of the solids analysis. And if we look at the various solids and species, we can kind of break that down into a number of operational definitions. There's the total solids. That's going to be everything in the water. The water then, operationally, we pass it through a 0.4 micron filter, and that separates the floaties from the dissolved. So we can kind of then break this and say, there's a total suspended solids, and there's a total dissolved solids. So TSS, that S is suspended. TDS, the D is dissolved. And the total dissolved solids simply is going to be the sum of all of our chemical species. We add up the milligram per liter of everything. That should give us the total dissolved solid.